we're going to start talking about a really important concept called the electric potential. We're going to get there by going through electric potential energy. Potential is again a concept we could have used for gravitation, but doesn't play that big a role. But for electricity, it ends up being really very useful. Do keep in mind it's a terrible choice of name, because now we have potential energy, which wasn't that great to begin with, and now we're just talking about the electric potential without reference to any other thing. Usually in English, potential is an adjective, but we're going to turn it into a noun. Apologize for that, and I'll go more on about that when we get to the actual thing. First, let's recall some results from mechanics. These are things that were true in mechanical systems and will extend but will still be true in electric systems. Any object of mass m that has a speed v also has a kinetic energy k, where k is 1/2 mv squared. This one you can probably do in your sleep. The work done by any force F that acts for a distance delta x at an angle of theta is just F times delta x times cosine of theta. All right, and again, that's saying if the thing honestly moves this way, but your force was constant and applied at this angle, then the work is F delta x cos theta. This ends up with a couple of important shortcuts or things we should remember. So if our force is along, we get plus and its maximum in work. If the force is angled but in the same direction, we get plus work. If the force is perpendicular, here we get 0 joules of work. If the force points somewhat backward, here we can see that our angle is more than 90, and that means our cosine will be negative work. Let's put work. And then if the force is directly opposed, then we will get negative work, and it will be the most negative work. Right? We want to keep those in mind, that if the force acts along, then we get positive work, and that if the force points opposite, we get negative work, and if the force is at right angles, we get 0 work. And why is that important? Because the total work done by everything in the system, everything working on an object, will change its kinetic energy, such that the total work done is the change in kinetic energy. This will especially be useful because we'll often just have the electric force, so it will also be the total work done. All right. For a so-called conservative force, we can define a potential energy U based on the work done by that force while the particle moves from point A to point B. So we have just an A and a B, and we take some path, and we define the potential energy such that the change in potential energy from A to B is minus the work done from A to B. Remember, of course, that delta always means this is U of B minus U of A. A force is conservative if any of the following is true. Each one of these implies the other, so if any one of them is true, they're all true. If the work done around any and every closed path is 0. So if I take any point and I say, hey, take any path, and no matter what path I pick, I get 0 work, then that force is conservative. Sort of logically enough, also it says that if the work done between 2 points depends only on the points and not on the path you take, so if the work done from A to B were the same along those 2 different paths, and it was true again for any paths that we took from A to B, then we would also say the force is conservative. A force is conservative if we can define a potential energy. So that was kind of goofy. And then the force is conservative if the force does not change the total mechanical energy of the system. That's where the name comes from, if it literally conserves the energy. The law of conservation of mechanical energy states, if only conservative forces act, the total mechanical energy of a system will not change, i.e. the thing we've done a lot. Kinetic energy plus the potential energy at the start is the kinetic energy plus the potential energy at the end. The electrostatic force is a conservative force. I'm not going to prove that to you, although it's not that hard, I don't think, but you can at least believe it because for point charges, it has the same form as the universal gravitational force. In other words, that Coulomb's law looks like Newton's law for gravitation, and we know that gravitation was conservative, so since this has the same form, it must also be conservative. All right, so consider the system shown here on the left, and consider a positive charge which is between the parallel plates of this capacitor. For that charge, for positive charge, where is the electric potential energy higher? Is it higher at A? Is it higher at B? Is it the same, or is there insufficient information? To answer, consider moving the charge from A to B. Since the electric force also points in that direction, the work done, right, because remember the field line tells us which direction a positive charge feels force, so the positive charge feels an electric force that is like this. The actual path, of course, is like this, which means that the capacitor does work on the positive charge, right? And the change in potential energy is opposite to that work. In other words, where does that work come from? It comes out of the potential energy of the electric field, right? If the change is negative, which means that UB is less than UA, then obviously UA must be higher. So it must be that point A is the higher potential energy. You could look at it a slightly different way, and maybe that would be useful. We know that since the force points along the direction the object's actually moving, it will accelerate the object. The particle will end up moving faster at B. If you let it go at A, it would move to B on its own. And so we know that that means it will gain kinetic energy, which would have to come out of potential energy. So the energy must be losing potential energy. To put that succinctly, in moving along a field line, a positive charge gets faster, gains kinetic energy, and so loses potential energy. Positive charges move from high to low potential energy. And that will be true for negative charges too. They will also move from high to low energy. But that's sort of annoying because we know that an electric field, a negative charge, if we put sort of a negative charge, would move this way against the field line, also moving to lower energy. So then for that case, we would have to have, for the negative guy, that UB is greater than UA. Even though for the positive guy, we had UA is greater than UB. And that's sort of annoying because we haven't changed the capacitor. We haven't changed the thing, just the thing we're testing it with. And yet we got these reversals of energy directions, and the reversal directions things move. So to flash forward a little bit, that's going to give us our concept of potential. We'd like to say, what is the capacitor doing? And then expressing it through the energy of the test particle we bring in. Analogously to how we defined field, so as to get rid of the test particle for the forces. All right, electric energy for point particles. Following the analogy between universal and gravitation and Coulomb's law, we can write an expression for potential energy between two electric charges Q1 and Q2, separated by a distance r. And that is, well, as given here. The electric potential of those two charges are Coulomb's constant times Q1 times Q2 over r. This is in parallel to universal gravitation, where the gravitational energy was minus big G mass 1 mass 2 over r. So we have, again, the same forms that are coming out. Notice we've picked some formulations here. This formulation says if two charges are infinitely far apart, they have no potential energy with respect to each other. In other words, if they're infinitely far apart, they're not going to interact. So it makes sense that they're not going to influence each other's movement. So that kind of makes sense. But do remember that potential energies can be defined 0 anywhere you want, because all we have really got formulas for are changes of potential energy. And that this is a particular choice where we say it's 0 when they're infinitely far apart. All right, if the charges have the same sign, the energy is positive everywhere. That's interesting, right? But you can just see K plus times plus is positive, or minus times minus is positive, and R, of course, is positive. So this whole thing is positive, which means there's always some potential energy. And the further you get, if we were to graph this, it would go as 1 over R. The further out you are, the lower the energy. Which makes sense because systems, remember, move towards or accelerate towards their places of lower energy. So if I put them this far apart and let them go, they will move outward so as to lower the energy, which means they'll repel, which is exactly what we'd expect. So that's pretty awesome. That worked out exactly the way we'd hope. On the other hand, if the charges are opposite sign, either plus and minus or minus and plus, then we would get the whole thing would look like this except for a minus, right? We'd have positive number times plus times minus, so the whole thing is minus, or positive number times minus times plus, whole thing is minus, over positive. The whole thing is a negative, and it looks like this. And that's interesting because that says that, well, remember, systems move towards, right? Let's label these. Systems accelerate towards lower energy, and this is lower energy than that. So systems will want to move along that curve, which means the particles will want to move to smaller separation, which means they attract, which is exactly what we expect. So this energy at least respects what we think about like charges and opposite charges. Like charges will repel. In this case, we can now say they repel because they lower their energy by repelling. And unlike charges attract because by getting closer, they get a more negative energy. So the energy again is decreased, and that's the way they want to move. All right. Here's a uranium example using uranium fission. So one possible decay path for uranium nucleus, say 92 protons and 143 neutrons, is into 2 palladium nuclei, each with 46 protons and 71 neutrons. Full disclosure, this is a possible decay path. It's not a common decay path. It requires things to line up really nicely, but it does happen that one uranium nucleus breaks into 2 palladium nuclei and some stuff. But let's assume the palladium nuclei start off at rest, which is quote unquote touching, which is separated by each by their own radius, right? So we have that distance and say that distance. The radius is 5.9 times 10 to the minus 15 meters. That's the radius of one of them, but of course they are separated by 2 radii. So they're separated by this number. And we want to say how much energy is stored in the electric field, which will tell you how much energy they'll give off when they repel, right? They'll repel and pick up a huge amount of kinetic energy and skitter far apart from each other and then deposit the energy somewhere else. So we're really saying how much energy is stored in the field at that moment, but really we'll express this as how much energy do we get out of this decay process. A couple of reminders. The atomic charge is 1.6 times 10 to the minus 19 coulombs, and each proton carries that. And the atomic mass unit is 1.66 times 10 to the minus 27 kilograms, and every proton and every neutron carries that. You could go and calculate that number for a sec, and then we'll see what comes out. It is pretty much plug and chug. Remember we have, this is K, and this is the charge squared because it's K, Q1, Q2. Oops, that was pretty terrible. Let's try that again. The energy is K, Q1, Q2 over R, but since the Q's are the same, we can just square it once, and we get 46 for each palladium atom. We get 46 charges, and then we square it. And likewise, down here we put the R, which is that, basically. And we get something like 4.1 times 10 to the minus 11 joules. And you're like, that's tiny. Like a joule is how much it takes to lift your textbook by 10 centimeters. This is 1/1,000,000th of that, or something along those lines. It's particularly tiny. But then, of course, the palladium nuclei are particularly tiny. They're nuclei. So we might want to consider the joules per kilogram released. In other words, how much do we get if we were to fission a whole kilogram of palladium? For anything like you moving at highway speeds, the energy per mass is about 340 joules per kilogram. All right, since we're doing kinetic energy there, the mass kind of drops out. And we say that if moving at highway speeds, you get about 340 joules per kilogram of object. That's why cars are so much more dangerous than you are moving at that speed, because they have much more mass than you. They'd multiply by a bigger kg. But for palladium nuclei, we have this energy divided by the mass. And if we look here, we have 46 and 171 is 117 total mass objects, and they get each of these. And here we get 2.11 times 10 to the plus 14 joules per kilogram. So we get something like 1 trillion times more energy density, if you want. The palladium comes out with 1 trillion times the joules per kilogram of a thing which is moving at, of say, a car. So if we talk about a 1 kilogram object, this thing would be obscene amounts of energy, which is why you get nuclear weapons, right? Fission of uranium produces a huge amount of energy, not per nucleus, but the density is so large that fissioning even a small number of nuclei will give you vast amounts of energy.